Hey, welcome to the answer to the questions from the Waves packet. Can't believe we're finally here, another year nearly done. Going to go through these. This is a fairly short unit, so this will be kind of quick. Reference table, we're going to be using page 1, page 3, and page 5, the modern physics section. Let's start with number 1. Moving electrons are found to exhibit properties of, well, this is a section on wave-particle duality. So even though it's an electron and not light, it still has both wave and particle qualities. So both particle and waves. That is called duality. Light demonstrates characteristics of, again, same thing, both particles and waves, depending on what experiment you do. Which phenomenon best supports the theory that matter has a wave nature? So waves will be like, we're talking about, matter. Let's look at this. Okay, because matter has a wave nature. Wave experiments include things like diffraction. So these are both diffraction. But other things like, let's think about this, Doppler effect, for example, interference, that sort of thing. But this is saying matter. So matter means we need to do particles with matter. So we're not talking about photon diffraction, which is a wave property, but that's for light. We're talking matter, so it's going to be electron diffraction. Both have wave-particle qualities. Okay, wave-particle duality is most apparent in analyzing the motion of, well, probably an electron, something very small. E equals mc squared now. The total conversion of 1 kilogram of the sun's mass into energy yields. Again, we're in the wave modern physics section, sorry. So we are now E equals mc squared. Note, this is not in electron volts or mega electron volts. Whenever we do E equals mc squared, it's going to be giving us joules. So E equals the mass, which is 1 kilogram, times c squared. C is 3 times 10 to the 8th meters per second. That's the speed of light. That is squared. So 3 squared is 9. 10 to the 8th squared is 10 to the 16th. All multiplied by 1 is still 9 times 10 to the 16th, except the units are different. They are now joules. You'll notice a joule is also a kilogram meter squared per second squared. So we get 9 times 10 to the 16th joules. There we go. If you wanted to convert that into electron volts or mega electron volts, you can go to the front page and you can see conversion from electron volts into joules, for example. Okay. Which graph represents the motion between energy and mass when matter is converted into energy? Well, energy and mass, E equals mc squared. So E is directly proportional to m. You can leave out the constant, so that should be a linear relationship. That's this, so it should be that, which means that the slope of that line, E over m, is going to equal, E over m is going to equal c squared. So the slope of that should equal the speed of light squared, 3 times 10 to the 8th meters per second squared. Okay, wow, a lot of words in a complicated diagram. Let's just start here and say, what statement best describes the changes that occur in this sequence of events? So let's think about it. Looks like an electron in E negative hits a particle that has E positive. I'm going to guess that has got to be a positron. So you have an electron and a positron, and they collide, and they release energy of some sort. And you can see a couple of mesons, which tells you mesons have both, there we go, quarks and antiquarks. Mesons have a quark and an antiquark. So in some way you have two particles hitting each other, releasing energy, releasing mesons, for example. So this is going to be some sort of matter turning into energy, but it looks like energy turns back into matter. So matter is converted into energy, and then energy is converted into matter. I think that's what that, okay. Isolated, and just to confirm, like energy is converted into matter, matter is converted into energy. That's not right, because we start with matter. That would be like annihilation right there, when particles collide and annihilate, and they create a lot of particle energy that is then creating other particles. Isolated quarks being formed from baryons. That's not right, because quarks don't live in isolation. quarks have non-integer charges that won't work. Hadrons are being converted into leptons. Mesons are not leptons. Leptons are totally different. Leptons include these things: electrons, muons, tau particles, stuff like that. So none of those are right, in case you're ever confused. I mean, it's a lot to digest, a big problem. So let's go slowly, and you can sometimes figure it out just by eliminating the other choices. The energy converted, so you're converting some mass, E equals mc squared. So the mass that you were converting is 2 times 10 to the negative 5th kilograms. C is the speed of light, 3 times 10 to the 8th meters per second squared. Left off units in there. Let's put this into the calculator. 2e negative 5 times, I'll use parentheses here, although 3e8 squared. It's going to give us a big number, 1.8 times 10 to the 12th. Now, it's giving that doesn't look remotely like any of these, right? But you do see a couple numbers with 1.8 and 1.8. So let's look at the first page of the reference table, the prefixes. So you see 10 to the 12th is our answer. Tera T is 10 to the 12th. So that is 1.8 times 10 to the 12th terajoules. That's answer A. A tritium nucleus is formed by combining 2 neutrons and a proton. The mass of the nucleus is, and it's giving us in universal mass units, less than the combined mass. Approximately how much energy is released. Okay, so when you're doing universal mass units, you cannot use E equals mc squared unless you want to convert to kilograms first. Much easier just to use dimensional analysis. It's kind of an ugly way to do it, in my opinion. But let's look at this. One universal mass unit is, and it gives us in mega electron volts. So we start with 9.106 times 10 to the negative third universal mass units. And we want to turn that into energy. Well, we can just use this relationship. We want to get rid of universal mass units. And we know that one universal mass unit is equal to a certain number of mega electron volts, MeV. And that would be 9.31 times 10 to the second. That is also 931. So 931 times this, and we know we did it right because the units cancel each other out. So we get 9.106 e negative 3 times 931 equals 8.47 mega electron volts. 8.47, and that's going to be in mega electron volts. So answer C, 8.48 if we round it up correctly. The energy equivalent to a rest mass of electron is approximately, okay. Well, notice all the answers are in joules, so that's probably E equals mc squared. E equals, let's take the rest mass, which is 9.11 times 10 to the negative 31st kilograms, times c squared, 3 times 10 to the 8th meters per second, and we get 9.11 e negative 31 times 3, don't forget the square, times 3e8 squared gets us 8.2 times 10 to the negative 14th. So that's answer B. Answers in joules. The energy equivalent of 5 times 10 to the negative third kilograms is, and again, answers in joules, E equals mc squared. So 5 times 10 to the negative third, you could write that as 5e negative 3 if you want, times 3e8 squared, mc squared, 5e negative 3 times 3e8 squared gets us 4.5 times 10 to the 14th. Answer C. Which graph represents energy and frequency? So now we are looking on page 5, because obviously for these graphs it helps to know an equation. So we know energy and frequency, E of a photon equals Planck's constant, which is on page 1, times frequency, E equals hf. So if this is the case and that's constant, E is simply proportional to F. That's a linear relationship. Looks like that. A variable light source emits photons As the frequency increases, what happens to the energy and wavelength of the photon? So as the frequency, so E equals HF. So it's a direct relationship. So increasing the frequency should definitely increase the energy. So as the frequency increases, the energy increases. So answer A and B are out. So then the question is, what happens to the wavelength? Well, we know, and I'm going to the wave section here, velocity is equal to frequency times wavelength. So that means, and velocity for this is just the speed of light, so you can put in c as a constant. So frequency is equal to speed of light over your wavelength. So that is an inverse relationship. As one goes up, the other goes down. So as your frequency goes up, your wavelength should go down. You could write that as wavelength equals c over frequency if you prefer. As the wavelength goes up, frequency goes down. As the frequency goes up, the wavelength goes down. So even though the energy increases, the wavelength decreases. Answer C. Photon has energy of E. Okay, so we know the wavelength. E equals, and we know the wavelength, so we're going to do hc over the wavelength. H is Planck's constant. We're going to look on the front page. You get this number down here that has the letter H. Planck's constant 6.63. E negative 34. Joule seconds, odd units, right? But they work out, trust me. C is the speed of light, 3e 8 meters per second. Not squared here, right? Over wavelength, and the wavelength is 6e negative 7. So now you just put it in your calculator. 6.63 e negative 34 times 3e 8 divided by, if you're not sure, put parentheses on 6e negative 7, and you get 3.3 times 10 to the negative 19th. Should be answer B. Next page. All photons in a vacuum have the same energy. No. Wavelength? No. Frequency? No. Speed? Yes. Right? Speed of light in a vacuum. There we go. Doesn't tell you a color or a frequency. It is what it is. Wavelength contains of photons having an energy of, okay, E equals energy of a photon is HF, or hc over lambda. So let's see, we know the wavelength, so it's going to be hc over lambda. 6.63 e to the negative 34th. (3e negative 8 over wavelength 5e negative 7. Make sure you put units in there if you need to. 6.63 e negative 34 times 3e, whoops, there's a mistake there. 3 times 10 to the 8th, 3e 8, not negative 8, divided by 5e negative 7. Gets us about 4 times 10 to the negative 19th. So answer C. Base your graph. Okay, the slope of the graph would be, see, it's funny, we don't need to read any of this in order to answer this question. The slope of the graph is energy over frequency. So E over F is your slope, Y over X, right? So let's figure out what E over F is equal to, because it's like, oh my gosh, how are we going to get these numbers? It doesn't even tell us, like it doesn't label axes. Like maybe you're thinking try to calculate the slope. Well, let's just look at the frequency. Let's look at the reference table for an equation. E equals HF. So if E equals HF, then E over F should equal H, which is your Planck's constant. So Planck's constant, then you can look it up. What is H? You see on the front page of the reference table, 6.63 times 10 to the negative 34th. Joules times seconds. It's all right there. Just understand that Y over X is your slope, and it will give you a value often based on the equations for what variable you're looking for, or constant in this case. The energy of a photon is inversely proportional to its, actually most of the time when you have a graph like this, your third thing, even if it's a variable, is always going to be constant, because otherwise these graphs typically wouldn't work. The energy of a photon is inversely proportional to its wavelength, speed, Well, everything travels at the same speed, so that's not it. E equals, inversely is going to be 1 over. So let's see, E photon, HF, there's nothing 1 over. There is HC over lambda. Inversely means it's proportional to what's underneath. So E is direct proportional to 1 over lambda, your wavelength. So that is an inverse relationship. The momentum of a photon. So even though momentum is mass times velocity and photons have no mass, you still have a momentum for your photon, h over lambda, where h is Planck's constant and lambda is the wavelength. Which equation shows the energy of a photon in terms of its momentum? So E equals h c over lambda. That is your equation. And I put it this way as opposed to E equals HF because we have H and lambda in this. So let's think, we just have to isolate this H over lambda times C. I just separated those because, you see H over lambda is P, is momentum. So it's just equal to P times C. So E photon is equal to PC. Photon of light definitely carries energy. Now, it has no mass, but it still does carry momentum, so it carries both energy and momentum. There we go. The charge to mass ratio of an electron. Weird question. It's like, oh, let's make you do pointless math. Just realizing charge to mass ratio is exactly what it sounds like. Charge to mass. So the charge is one elementary charge, 1.6 times 10 to the negative 19th coulombs. The mass is, and if you're not sure about any of this stuff, make sure you get the units right. It's going to be C over kg. The register mass of an electron is 9.11 times 10 negative 31. Negative divided by a bigger negative exponent is going to be a positive. So, I mean, that right there, it's not going to be A or B. But let's 1.6 E negative 19 divided by 9.11 E negative 31. And we should get the right answer, 1.76 times 10 to the 11th. Don't get confused with the 10 to the negative 11th. Okay. An energy electron in the C level of Mercury. So we're going to look at Mercury. C level right here. C goes to B or A, or you can also have a B to A transition. So what photon energy could not be emitted? So C to B gets us negative 5.52 minus negative 5.74. So that becomes negative 5.52 plus 5.74. So C to B is 0.22 eV. B to A is equal to, let's see, negative 5.74 minus a negative, so it becomes plus 10.38. So B to A is 4.64. And you can have C to A. So C to A is going to be negative 5.52 minus a negative, so plus 10.38. And this should be 4.86, the biggest of all. 4.86. So we have three choices, 0.22. That's right there. So that could be emitted. 4.64 could be emitted. 4.86 could be emitted. So what is not? 5.43 electron volts. So a little bit more work for this because we have to do the subtraction 3 times, but this is pretty easy math. You really need to know how to do this. An electron in a mercury level drops from F to C by emitting a photon. So E initial minus E final. By the way, didn't say it last time. That's this equation here. E photon is EI minus EF. Remember this first equation, E equals HF? That's always going to be in joules. This is always going to be in electron volts. So EI minus EF. So we have mercury here. Level F has got negative 2.68 minus a negative. Let's go into level C. 5.52, so that becomes a plus right there. So you get negative 2.68 plus 5.52. It's me 2.4 electron volts. Okay, the statement. The spectrum of visible light emitted during transitions in an excited hydrogen atom is composed of blue, green, red, and violet lines. What characteristic of light determines the amount of energy carried by a photon of that light? Interesting. This is pointless information for this particular question. Let's see if it's useful for the next one. What determines the energy carried by light is going to be the frequency. E equals H times F. What color of light is the visible hydrogen spectrum? Let me pause. Okay. What color of light in the visible hydrogen spectrum has photons of the shortest wavelength? So, interestingly, we don't even need this question, this reading to answer either of these questions. It has the shortest wavelength. Well, if you're not sure, we can actually look at page 2. It wasn't one that I initially pointed out, but sometimes it's not uncommon to use this. So we want to find the shortest wavelength. So here is visible light. Notice it's the bottom here. This is frequency. So this is the biggest frequency, which means that if this is the big frequency, this is a big wavelength. And you can look at the top and see the further to the right you get is the biggest wavelength. So the shortest wavelength is going to be the biggest frequency. So having said that, it's going to be violet right there. Photon has 9.4 electron volts and it hits an hydrogen atom. Why is the photon not absorbed by the hydrogen atom? So we got to look at a hydrogen atom and say, hey, well, what does 9.4 volts get you? And perhaps it's the wrong amount of energy. So how much energy, for example, do you need to get from n equals 1 to n equals 2? EI minus EF is going to be equal to initial negative 13.6 minus EF 3.4. So that's a plus. So you take 13.6 and negative 13.6, I should say, and add to it 3.4, and you get negative 10.2, meaning it absorbs 10.2 electron volts of energy to get from N1 to N2. But it's only getting 9.4, so that's not enough energy to jump. So that electron is not interested in that particular packet of light. It needs something that is more energetic, that has 10.2 electron volts. So the photon's energy is going to be too small. Is it photons repelled by electrostatic force? No. The orbital is moving too fast? No. The photon strikes the atom moving too fast? No. Photons strike at the same speed every single time, at least in air. Which type of photon is emitted when an electron drops from N2 to N1? So let's go N2 to N1. So initial minus final, N2 is negative 3.4 electron volts minus a negative 13.6 electron volts. Subtract those two and you should get 10.2 electron volts. Now you might be like, oh gosh, I don't know, because that's still something weird. So let's take electron volts, and this is an annoying step we have to do multiple times in this. Let's figure out what the frequency or the wavelength is. So we can just do frequency, right? But before we do that, we actually have to convert that to joules, because we're going to use this equation, equals HF. But before we do that, we need that energy in joules. So you want to take electron volts and turn it into joules. We know 1 electron volt, put that on the bottom because the units cancel out, is equal to 1.6 times 10 to the negative 19th joules. So you get 1.6 e negative 19 times 10.2 gets me 1.632 times 10 to the negative 18th joules. which is equal to h times frequency. So frequency is equal to this divided by h, and h is, it's going to be energy divided by h. So take that number, divided by 6.63, E negative 34, which is your h, your Planck's constant right there. 2.46 times 10 to the 15th hertz. Okay, so let's think about this. What is 2.46 times 10 to the 15th hertz? You probably don't know it, but you've got this table. Frequency is in hertz. You're looking at 2 times 10 to the 15th. So let's see, these are all 10 to the 14th. You'll notice they get bigger as you go to the left. This is 10 to the 15th, so the number we're looking at is a little bigger than 10 to the 15th. Boom. So it's right around there. It should be in the ultraviolet. Ultraviolet. Okay. A hydrogen atom, when the N2 is excited until you get into the N4. So what happens? So if you go from N2 to N4, you must first of all absorb energy, right? Because you're going from a low to a high level. You're climbing upwards. So in that case, you know that it's not emitting. So it's got to be A or B. N2 minus N4. So let's look at your reference table. Initially, it starts out with negative 3.4 minus a negative 0.85. So you get negative 3.4 plus 0.85. And that gets us 2.55. So negative, technically a negative 2.55 electron volts. That negative is another sign that it is absorbing it. So it absorbs, answer C, 2.55 eV photon. Mercury drops from energy level I to the ground state. So negative 1.56 is its starting energy minus a negative 10.38. So we get 8.82 electron volts. That would be answer B. So it emits a photon with that much energy. Mercury in the ground state absorbs 20 electron volts and is ionized. How much kinetic energy does the electron have after the ionization? Okay, so this is challenging, but if you recognize energy is conserved, let's just see how much energy it takes to ionize mercury. So mercury in the ground state has negative 10.38, so that's going to be its initial energy, 10.38. Now if it's ionized, when you subtract something, ionization gives it 0, minus a negative 0. I'm sorry, minus 0. Subtract those both and you get negative 10.38 eV, which tells you it needs to absorb that much energy. So if it needs to absorb that much energy, but it actually absorbs 20, it's got way more than it needs. So let's take a look and see how much extra it gets. 20 minus 10.38 tells you that it has 9.62 extra. So that 9.62 is turning into kinetic energy. 9.62. Tricky problem there. Bright line spectra of 4 elements, A, B, C, and D. Based on comparisons, which 2 elements are found in the unknown sample? So this unknown is made up of different elements. Let's look. Is A, those are the lines for A. Do those appear in there? No. Don't seem like it. This one's kind of close to there, but there's no lines there. This, boom. This, boom. So those 2 lines both appear, so it's got to have B. C, you look. There is a line. There is a line. There are 2 lines there, so it looks like C is also in there. D, there's no lines there. There's no line there. There's no line there. So it's got to be B and C. It's the answer C. Okay, let's keep going. How much energy is required to move an electron in a mercury atom from the ground state to energy level H? So mercury ground state starts with negative 10.38 minus a negative, let's say it ends up in H, 1.57. So negative 10.38 plus 1.57 gets us a total energy of negative 8.81 electron volts. Negative means it's absorbed, so that means that's how much energy it needs to absorb. A bright line spectrum is an element, okay. So bright line spectrum is those bright lines that we saw, just kind of like on the last page when we looked at this is a bright line spectrum. There's lines at all these different points. We know that as a result of electron transitions between discrete energy levels in the atom of that element. So I think that would be A. It's not about protons acting as particles or waves or electrons in the nucleus, which isn't true, or protons being dispersed. Okay, if you're in the 3 state, how many different photon levels could be emitted as you return to the ground state? Well, you could go from 3 to 1 directly, but you could also go from 3 to 2 and 2 to 1. So that's three different jumps, and so 3 different lines. Answer C. The slope of a graph of energy versus photon frequency represents. So E versus frequency, E versus F. Say you have a graph, the slope of that is going to be E over F. We see, if you look at the reference table, E equals HF is that equation. So E over F is equal to H. So that would be Planck's constant. H is your Planck's constant. Particles are held together primarily by in the nucleus. So it's not gravity, right? It's definitely not electrostatic because there's positive particles. They would repel each other. This force that is in the nucleus is the strong force. The weak force is responsible for radioactive decay. And magnetic forces are related to electrostatic forces. They probably should be separate. 38 and 37, we got a table. We got a proton, up, up, down, antiproton, UUD, neutron, UDD, lambda, UDS, omega, SSS, and it's got different charges, right? You notice that all 3 of these are made up of 3 quarks, or in this case 3 antiquarks. So having said that, let's look at this. Mesons are made up of quark and antiquark. That's not the case. Hadrons are made up of baryons and mesons. So if mesons are not, then they can't all be hadrons either. Well, I take that back. 3 quarks is all going to be 3 baryons. I'm need to be careful about how I read this question. So if they are made up of 3 quarks, that means they're all baryons, and all baryons are hadrons. So I take that is a valid answer. Let's just confirm. Are they all antimatter? No. The only one that's antimatter are the ones with the lines, the antiproton with an anti-up, and anti-up, and anti-down. Leptons. Are they all leptons? No. Leptons are electrons, muons, tau, and these 3 types of neutrinos. Which particle listed in the table has the opposite charge of and is more mass than a proton? So let's look at this. A proton, 0.938. So it shouldn't be an antiproton because an antiproton has the opposite charge, that's true, but it has the same mass. A neutron does not have the opposite charge. A neutron has a little bit more mass. So let's look and see an omega. No, yeah, omega, there we go, -1. And mass is 1.6. So it has the opposite charge and has more mass. So that would be the correct answer. I'm sorry. I'm saying omega, but I'm looking at lambda. Or this says lambda. Lambda has no charge, so it's not that. Omega, yes. Opposite charge of a proton and has more mass. Baryons can have a charge of. So this is a baryon right here. Baryons are made up of 3 quarks. So those 3 quarks can have charges of -2, -1, 0. Oops, sorry. Let me correct. -1, 0, 1, and 2. Because baryons are made up of 3 quarks. So 3 quarks, if these are your quarks, can add up if you have like 3 tops or 3 from the top level. 2/3 plus 2/3 plus 2/3 is 2. Up to -1, because you can only have a -1/3 plus 1/3 plus 1/3 is -1. You're not going to have fractional charges. So some things like that and that are just directly out because you can't have fractional charges. So is it -1 and +1? That's possible. 2 and 3, that is not possible. You cannot have a charge of 3e. So answer is going to be C. What's the total number of quarks in a helium nucleus consisting of 2 protons and 2 neutrons? Well, each baryon, because these are baryons, have 3 quarks. So you have 3 quarks, and you have 1, 2, 3, 4 particles, each of which has 3 quarks. 4 times 3 is 12. Answer B. What fundamental force holds quarks together to form particles such as protons and neutrons? We are looking. Wait, let me pause this for just a second. Okay, where was I? What fundamental force holds quarks together? Okay, so quarks are going to be like protons and neutrons, which are in the nucleus of an atom. And if you're looking at the force that holds together a nucleus, it's going to be the strong force. Electromagnetic, no, because you're not going to have protons being attracted to other protons. Gravitational force, no, way too weak. And the weak force is, interestingly enough, stronger than the gravitational force, right? But it's more responsible for radioactive decay. A top quark has an approximate charge of, ugly question, because a top quark has a charge of 2/3 E, and E is a charge of 1.6 times 10 to the negative 19th coulombs. So it's really this. I don't like this because now we're dealing with fractions, and it makes it sound like it's something plausible that you can have, when it really isn't. 1.6 times 10 to the negative 19th. You don't really have top quarks just existing out there on their own. So there we go. So you get 1 times 10 to the negative 19th, 1.07. And the top quark, let's make sure, has a positive charge. So it's going to be positive 1.07 times 10 to the negative 19th. It is what it is, but recognize that this doesn't exist in nature. And if you see this, normally you're going to say, hey, that is not a possible charge, because you need to have charge quantized. It has to come in increments of E, which is to say 1.6 times 10 to the negative 19th. So 1 times that, 2 times that, 3 times that, etc., etc. Okay. According to standard model of particle physics, a meson is composed of, let's look at mesons, a quark and an antiquark. A quark and a muon neutrino, no. A quark and an antiquark, yes. 3 quarks, no, that's a baryon. A lepton and an anti-lepton, no. What is the sign and charge in coulombs of an antiproton? So, we're still in multiple choice questions. An antiproton, so it's going to be opposite of a proton. So a proton has a +1 charge. For an antiproton, it's going to have a -1 E charge. That's it, -1. Now -1 E is -1.6 times 10 to the negative 19th coulombs, if you want to put it in coulombs. And the answer says coulombs. Interestingly enough, that is the charge of an electron, too. Okay. Which statement is true of the strong nuclear force? So, the strong nuclear force tends to hold together the nucleus of an atom, so it holds protons and neutrons together. The tau neutrino, muon neutrino, and the electron neutrino are all, let's look at the reference table, boom, leptons. A meson may not have a charge of, so mesons are a quark and an antiquark. So at most you can have a positive 2/3 and a positive 1/3, because you can't have a fraction. You can't have like an up and an anti-charm. No, that would add up to 0. I mean, that's possible, but so at most you can go to +1. At least you can go to -1 E. You can also go to 0. So any of those 3 charges are fine, but you cannot have 2E. You could, if you were a baryon, have a +2E. A particle unaffected by an electric field could have a quark composition of. Okay, so electric fields create a force on electrically charged particles. So let's see what the charge of these is. CSS. So that's 2/3 minus 1/3 minus 1/3 totals to 0. BBB is going to be -1/3, -1/3, -1/3, totals to -1. UDC is 2/3 minus 1/3 plus 2/3. 2/3 minus 1/3 plus 2/3 is going to equal 1e. UUD is 2/3, 2/3, and down is minus 1/3. So that is going to be 1e. By the way, that's a proton. Because remember, U and D make up the most basic materials are U and D. So protons and neutrons are made up of U's and D's. So if a proton is got a positive 1 charge and it's only made of U's and D's, then that's got to be a proton. Protons definitely are affected by electric fields. You want something that has 0 electric charge, so that would be CSS. That would be 0. Lithium has 3 protons, 4 neutrons, and 3 electrons. Let's think about this. 3 protons are all baryons, right? So 3 protons each have 3 quarks in them. 4 neutrons are also baryons. They also have 4 quarks in them, 3 quarks in them. So you add those up. 3 times 3 is 9 quarks. 4 times 3 is 12 quarks. So you have a total of 21 quarks. 3 electrons. Electrons are leptons. So you have 21 quarks and 3 leptons. Answer D. Okay, a lambda particle consists of an up, a down, and a strange. Can be classified as up, down, and strange are 3 quarks. Anything that's made of 3 quarks is a baryon. So they are baryon, which would also be a hadron, but not a meson, and not a lepton, and not a photon, which is light. What is the charge of a lambda particle in elementary charges? So lambda is up, down, strange, UDS. Up is 2/3. Down is minus 1/3. Strange is minus 1/3. Add those together. 2/3 minus 1/3 minus 1/3 is 0. So 0 elementary charges. If you want it in coulombs, it's 0 coulombs. According to the Standard Model, a proton is constructed of 2 ups and 1 down, UUD, and a neutron is constructed of an up and 2 downs, UDD. During beta decay, a neutron decays into a proton, an electron, and an antineutrino. During this process, there is a conversion of, let's see, I'm going to write this out because this gets kind of confusing. A neutron, which starts out as U, DD, becomes a proton. A neutron becomes a proton. So UD. So it starts with a U and 2 Ds, ends with 2 U's and a D. So clearly that D in some way, one of those D's has to become a U. So you get a down quark that is going to become an up quark in some way. So is it a U becoming a D? No. Is it D becoming a meson? No. We're not dealing with mesons. They all have 3 quarks. So we need to get, is it a baryon to another baryon? Well, a baryon is 3 quarks. This is 3 quarks. That's a baryon that turns into another baryon. So that seems like that's the right answer. Answer C. Is it a lepton to a lepton? No. Which could produce a neutral baryon? CDT. Charm. Down top. So 2/3 minus 1/3 plus 2/3. Add those together. You get 3/3. So that's 1e. That's not the answer. CTS is 2/3 plus 2/3 for top. And the strange is minus 1/3. That's also 1e. That's not the answer. CBT, 2/3 minus 1/3 for bottom, and minus 1/3. So 2/3 minus 1/3 minus another third is equal to 0e. That seems like the right answer. CDU. So C is 2/3, D is minus 1/3, U is plus 2/3. Add those up, and those also add up to 1. So the one that adds up to a neutral charge with 0 is CBD. Okay, so now we're getting into some extended response questions. I am not going to do that right now. That'll be a separate video.